Hello, I am Caterina Urban, and this is a review of the state of the art in formal methods for robust artificial intelligence. The main differences between artificial intelligence software and traditional software arise essentially from the software development process. Artificial intelligence software is developed in pipelines, which begin with the collection of data and its preparation and pre-processing for training. It is followed by a training phase of a machine learning model and ends with the deployment of the trained model, and it's used to make predictions and to automate tasks. The problem is that the training phase is highly non-deterministic, which offers no predictability or traceability of the software development process. And moreover, the trained models only give probabilistic guarantees on the prediction results, which are bound to the data used for training. And this is clearly not sufficient for guaranteeing an acceptable failure rate under any circumstances. So, of course, this becomes a problem, especially since artificial intelligence nowadays is slowly creeping even into safety critical applications like healthcare or the automotive industry and so on. And these applications require an extremely high level of assurance that the software always behaves correctly and reliably. So for this reason, researching formal methods for the development and assurance of machine learning systems is now rapidly gaining popularity, mostly driven by the needs of the automotive and avionics industries. And the attractive aspect of formal methods is that they provide strong and mathematically grounded guarantees on the software behavior. So we can broadly divide formal methods in three categories. The first is the family of deductive verification methods, in which the user provides a formal specification for the software, and the specification is expressed generally in some logic language. And the verifier then propagates the specification through the program using, say, symbolic execution or weakest preconditions. And this way generates verification conditions implying that the program obeys its specification. These verification conditions are then proved correct using some SMT solver generally. So the main advantage of deductive verification is that it can handle extremely expressive specifications. On the other hand, however, the user often has to guide the correctness proof. It has to provide invariants or other annotations that make the verification conditions tractable for the underlying solver. Another class of formal methods are model checking approaches, which offer sound and complete verification of a model of the software, and they do so by exhaustive state space exploration. The problem is that crafting a faithful model that can also be efficiently checked is not always easy. And even then, soundness and completeness only hold with respect to the model and not the original software. More recently, software model checking allows the direct verification of the software without requiring a handcrafted model, but has to make compromises to sidestep the intractability of an exhaustive exploration of the state space. So, for instance, bounded model checking limits the exploration to execution traces of a fixed length, and in this way loses soundness and completeness with respect to the entire executions, a set of executions of the program. Other software model checking approaches instead might not terminate in some cases. Finally, we have static analysis methods, which directly verify the software at some level of abstraction, focusing only on the software properties of interest. So these approaches are fully automated and guarantee soundness by over-approximating the set of possible software behaviors. On the other hand, because of these over-approximations that they do, they are inherently incomplete. And for this reason, the verification can fail in some cases because of the over-approximation. So the software actually satisfies the desired safety property, but the static analysis is unable to prove it because the over-approximation is too coarse to conclude. I would say that formal methods for artificial intelligence software developed so far mostly belongs to either the model checking or the static analysis families, or are somehow a combination of the two. So in this review, I will focus on where the majority of formal methods for artificial intelligence software have been applied, which is the verification of trained neural networks. And in particular, in the rest of the talk, I will assume that we are verifying feed-forward fully connected neural networks with ReLU activation functions, which are the only models supported by all methods in the literature. And for simplicity, let's say that neural networks have a single output, and we want to verify a safety property which specifies a bounded input domain. So it gives lower and upper bounds for all inputs of the neural network and requires the output of the neural network to be a positive value. So let's start by looking at model checking like methods. So these can be further subdivided into methods based on SNT solving and methods based on mixed integer linear programming. So SNT-based methods essentially reduce the verification problem to a constraint satisfiability problem. So a given neural network is directly modeled by constraints which encode the, on the one hand, the affine transformations performed by the neural network layers, and on the other hand, the ReLU activations. So we have these non-linear constraints that model the ReLU activations. We can then conjoin these constraints with the input specification and the negation of the output specification. So in our case, the output specification asks the output of the neural network to always be a positive value. So the negation requires the output to be smaller than or equal to 0. Now, if we can find a value assignments for the variables of this SMT problem, a value assignment that satisfies all of these constraints, then we have a valid, we say that this SMT problem is satisfiable, and the value assignment gives a valid counterexample to the safety property. So we have a proof of violation for the safety property, which gives us an indication of why the property is violated. Otherwise, if the problem is unsatisfiable, we are sure that the safety property is verified. I'll give you now a couple of examples of methods that use this approach. So the first example is Planet. The underlying idea of Planet is to use approximations to reduce the search space for the SNT solver. In fact, the SNT problem with these constraints that are nonlinear becomes an NP-complete problem. And so Planet, to reduce the search space, replaces these nonlinear constraints with this triangle-like approximation of ReLUs, which consists of these three linear constraints. And the search for a solution for the SNT problem is then done by fixing the activation status of the ReLUs and backtracking when needed, so when the constraints become unsatisfiable, until the entire search space is exhausted. And so the approach can conclude whether the property is actually satisfied. Another example is ReLUplex, which underneath is based on the simplex algorithm, which is extended to support the ReLU constraints. So the idea of ReLUplex is to maintain a value assignment for all SMT problem variables, even if this value assignment violates some of the constraints of the SMT problem. Then, at each step, this value assignment is modified in order to fix some of the violated constraints. Now, if some ReLU constraints get fixed too often, they're split in two cases, each corresponding to a possible ReLU activation status. So we are going to have a case for the active status of the ReLU and a case for the inactive status of the ReLU. All this continues until a counterexample for the given safety property is found or the safety property is verified. The successor of ReLUplex is called Marabou. Additionally offers a divide and conquer solving mode, which iteratively splits the input space. And so it naturally lends itself to a parallel execution. Also, Marabou is able to prune the search space for ReLUplex, essentially for the ReLUplex approach, by maintaining symbolic lower and upper bounds for all neurons in a neural network. And the symbolic lower and upper bounds are essentially linear combinations of the inputs. In the literature, there are other SMT-based methods. For instance, the work of Polina and Tacchella, which is the very first formal verification methods proposed for neural networks. The work of Bastani and others for finding the nearest adversarial example with respect to the L-infinity distance, so the closest input that produces a different output of the neural network. The work of Wang and others for proving local robustness to adversarial perturbations, so proving that in a neighborhood of a given input, there are no adversarial examples. So all the inputs in this neighborhood are produce the same output. And the work of Naroditska and others, as well as Cheng and others, which instead focus on binarized neural networks. Okay, so now the other model checking like approaches are those based on mixed integer linear programming, and these reduce the verification problem to a mixed integer linear program. So in particular, ReLU activations are encoded using binary variables to represent their activation status. So whenever these variables have value 1, the ReLU is active, so it has a positive value. And whenever these variables have value 0, the ReLU is inactive, so it has a negative value. Then in the encoding, in addition to the specification of the safety property, there generally also is an objective function that one wants to minimize or maximize. So in our case, for instance, we could minimize the value of the output node of the neural network. Now, if the value of this objective function is negative, this gives a counterexample for the safety property. So again, a proof of violation of the safety property. And otherwise, we know that the safety property is verified. So this encoding here is very general. In practice, what people do is they limit the bounds of the variables of this optimization problem. In this way, they speed up the verification because they are able to prune the solution search space. So one of the possible bounded encoding uses symmetric bounds for each neuron in a neural network. And these bounds are essentially the maximum between the concrete upper bound of a node and minus the concrete lower bound of a node. So this is the bounded encoding with symmetric bounds. And this is the encoding that, for instance, Sherlock uses to establish a value range for a neural network output. So let's say, for instance, that we want to find the lower bound of the output. So we're gonna minimize the output of the neural network. What Sherlock does is it combines the mixed integer linear programming with local search in order to speed up the solver, the mixed integer linear programming solver. So in practice, the analysis starts with a random input, X, and its corresponding output, let's say we call it L. This L is then given to the solver as a target lower bound. So the solver is asked to find a solution with a better lower bound than this given L. If the solver is able to find such a solution, then the local search is used to find another input, let's say X hat, with a better output lower bound than the solution found by the solver. In particular, local search uses gradient descent over the neural network and searches in the input space that activates the same ReLU activations of the solution found by the solver. If such an input X hat is found, then the solver again is invoked with an updated target lower bound, and so on until the solver is able to conclude that no better solution exists. Now, a better bounded encoding actually uses asymmetric bounds for the problem variables. So it uses the concrete upper bound here and minus the concrete lower bound here, and this gives tighter. These bounds are tighter actually than those used in the previous encoding, so they are better bounds. This encoding is more precise, essentially. And this is the encoding used, for instance, by MIP-verify to find the nearest adversarial example, X prime, with respect to a given distance metric, such as the L1 or L2 or L infinity distances. So essentially the input that is closest to a given input X and produces a different output of the neural network. And MIP-verify, to determine these concrete lower and upper bounds that are needed in the encoding, uses a progressive bound tightening procedure. So initially it uses interval arithmetic to quickly find coarse bounds. Interval arithmetic is very cheap, but the bounds found with interval arithmetic can be rather imprecise. If these bounds are not sufficient to determine the activation status of some ReLU activation, then MIP-verify uses a linear programming solver to find tighter bounds, and it does so by essentially minimizing and maximizing the value of the corresponding neuron. In the literature, other mixed integer linear programming approaches are, for instance, the work of Bundel and others. They propose a unifying safety verification framework for neural networks with piecewise linear layers and ReLU activations. And in fact, they show that such a framework encompasses other approaches like Planet as well as ReLUplex. Another work is the work of Cheng and others for finding a lower bound on robustness to adversarial perturbations, which is the largest neighborhood in which no adversarial examples exists. And finally, the work of Fischetti and Joe for feature visualization or for building adversarial examples. Okay, so let's move on now to static analysis methods. So these are essentially based on abstract interpretation. So the idea is to start with an abstraction of the input specification in some abstract domain, propagate this abstraction forward through the neural network to ultimately obtain an over-approximation of the neural network output. We can then check if this over-approximation is included in the output specification. And if so, we know that we have verified the safety property, because that means that the actual output of the neural network is also included in the output specification. So that means it also satisfies the output specification. And otherwise, we're going to raise an alarm, which, of course, it could be a false alarm caused by the over-approximation. So the neural network might satisfy the safety property, but this over-approximation is too coarse to conclude, to verify that this is the case. So a simple example of abstraction that has been proposed in the literature maps each neuron to concrete lower and upper bound, as well as a symbolic expression, which is a linear combination of the input neurons and ReLUs in previous layers. So we do the analysis of the neural network with this abstraction. So whenever we encounter an affine transformation performed by the neural network layers, we simply propagate the symbolic expression. So we replace the variables occurring in this affine transformation with the corresponding symbolic expressions. And in this way, we are able to determine tighter, lower, concrete lower and upper bounds for neurons in deeper layers. This is because we maintain some dependencies between neurons in previous layers. So in this way, maybe some expressions cancel away and we find better lower and upper bounds. Instead, for ReLUs, we have various cases depending on the activation status of the ReLU. So if the ReLU is active, so that means that the value before the ReLU is already positive, then we're essentially doing nothing. The concrete lower and upper bounds remain unchanged, as well as the symbolic expression. The other case is when the ReLU is always inactive, so its value is negative. In this case, everything is set to 0. And then finally, we have the case of an undetermined ReLU, so a ReLU with an undetermined activation status, with a negative concrete lower bound and a positive concrete upper bound. So in this case, we set the concrete lower bound to 0, and we replace the symbolic expression with a fresh symbolic variable that represents the ReLU in subsequent layers. So in subsequent layers, the symbolic expressions will use this variable, which corresponds to this concrete lower and upper bounds. A more precise abstraction is instead the deep poly domain, which also maintains concrete lower and upper bounds, and additionally, it maintains symbolic lower and upper bounds for each neuron, again as linear combinations of neurons in previous layers. Now, in the case of ReLUs with an undetermined activation status, what Deep Poly does is it uses two different two different convex approximations for the ReLU. So one is this one here, and one is this one here. So the choice between these approximations is given by the approximation that essentially minimizes the area in this input-output plane. So basically, whenever the concrete upper bound is smaller or equal than minus the lower bound, we choose this first approximation. So we set the lower bound to 0 and the upper bound to this symbolic expression here. And otherwise, we use the second approximation where the lower bound is x before the ReLU and the upper bound is again the symbolic expression here. In either case, this approximation partially keeps dependencies with respect to input neurons or neurons in previous layers, and they are thus more precise than the simple symbolic propagation, which essentially forgets anything that happened before it encountered this ReLU with an undetermined activation status. So in the literature, we have, of course, other abstract interpretation methods. So one is, for instance, the AI squared framework proposed by Gare and others. And this is the first use of abstract interpretation for verifying neural networks. We have the Deep Z domain, which is a custom zonotop abstract domain, which is tailored for neural networks. So in particular, this domain is equipped with special transformers able to handle different ReLU activation functions. We also have the K-ReLU framework proposed by Singh and others. This framework allows for the approximation of K ReLU activations all together, all jointly together. And this way, this allows for a more precise approximation of a transformation performed by a layer of the neural network. And then finally, we have my work with my co-authors on verifying fairness of neural networks used for classification of tabular data. In the literature, there are also other methods that I would say are essentially static analysis methods, but they are also complete. One such method is, for instance, the star set approach, which uses an exact representation of all possible values of a neuron. And this representation is, in practice, an alternative representation of bounded convex polyhedra. But unlike polyhedra, this representation offers fast and cheap affine mapping operations. So this way we can quickly analyze the affine transformations performed by neural network layers. And it also offers inexpensive intersections with half spaces. And this allows modeling the ReLU activations. So essentially, the analysis with star sets maintains a union of star sets to precisely model the ReLUs with an undetermined activation status. So essentially, whenever we encounter a ReLU that is undetermined, we split a star set in two, one for each possible activation status of the ReLU. So the analysis starts with an exact representation of the input specification and propagates this abstraction through the neural network, splitting it in 2 or 4 and so on if necessary, depending on the ReLUs that is encountered, until at the end, the output of the neural network will have the exact reachable set of the neural network, which can then be used to check the output specification. In follow-up work, Tran and others further generalize the star set representation to image sets and use them to verify convolutional neural networks. Okay, another example of complete static analysis approach is ReLUVAL, which is essentially an asymptotically complete static analysis method. So ReLUVAL uses symbolic propagation, simple abstraction that we have seen before, but also iteratively refine the input space whenever necessary. So specifically, whenever the output over approximation is too large to be conclusive, so whenever the analysis raises an alarm, ReLUVAL splits the input space in half and repeats the analysis on the resulting smaller input spaces. In particular, the split of the input space is done along the dimension that influences the most the neural network output. And so such refinement process is then guaranteed to converge in finite steps because the over approximation error decreases as the input space gets smaller. The successor of ReLUVAL is called NeoRefi. Instead of symbolic propagation, uses a more precise abstraction, which, like deep poly, maintains concrete and symbolic lower and upper bounds for each neuron. But for undetermined ReLUs, it uses a different convex approximation. And additionally, what NeoRefi does is to minimize the error introduced by this approximation by iteratively splitting also on the over-approximated ReLUs. And in particular, it splits the ReLUs that have the largest output gradient. So again, the ReLUs that have the most influence on the output of the neural network. In the literature, other complete methods are the work, for instance, the work of Ruan and others, which is based on global optimizations, and the refined Zona framework proposed by Singh and others, which combines abstract interpretation and mixed integer linear programming. And finally, other incomplete methods are based on directly abstracting neural networks, so the model itself, rather than the computation performed by the model. So these methods essentially compute a smaller neural network, which over-approximates the output of the original one. So an example of such an abstraction are interval neural networks. The idea of this abstraction is to merge neurons layer-wise according to a given partitioning strategist and replace the weights of the neural network with interval weights in such a way that they soundly account for the merging, and so they make sure that the output of this smaller neural network is an over-approximation of the original one. The safety verification then can be conducted on the smaller interval neural network using essentially any of the existing approaches, provided that they are adapted to support interval weights. So in particular, in the paper, the authors use mixed integer linear programming. Another abstraction has been recently proposed by El Boher and others at CAV this year. And this abstraction merges neurons according to the sign of the weights on their outgoing connections and their effect on the neural network outputs. So it essentially partitions the neurons of the neural network according to these characteristics, and then only merges neurons that belong to the same partition. So other incomplete methods in the literature, there are many. There is the work of Xiang and others, for instance, which combines simulation and linear programming, again for safety verification of neural networks. The work of Vijotam and others, which is based on duality, and a number of different approaches for finding a lower bound on robustness. So again, this the largest neighborhood in which there is no adversarial examples. And these approaches are based on duality or semi-definite programming or on bounding the Lipschitz constant of the neural network and so on. So there are very different approaches. We also have extensions of these approaches that actually support convolutional neural networks or recurrent neural networks. We have the work of Zhang and others for safety verification of recurrent neural networks. And finally, the work of Gopinath and others for inferring safety properties of neural networks. Okay, so now let me conclude by generally comparing complete and incomplete methods for artificial intelligence software. So complete methods are both sound and complete, so they can precisely report whether or not a given safety property holds for a neural network, and they generally are able to provide a counterexample in the latter case. And such a counterexample is very valuable in determining the cause of the safety violation, of course. On the other hand, however, soundness is not necessarily or typically guaranteed with respect to floating point arithmetic, but only with respect to computations in the reals, which might not correspond to the actual computation performed on a computer machine. Complete methods are also not generally able to scale to large models, and they are limited to certain model architectures, for instance, neural network with ReLU activations or neural network with certain kinds of layers and so on. Incomplete methods, on the other hand, are able to scale to larger models, and they are less limited to certain model architectures. So we have seen that there are some approaches that are also able to handle a recurrent neural network, for instance. And incomplete methods are also sound, often with respect also of they are sound often also with respect to floating point arithmetic, or in any case are easy to render sound using standard approaches that exist in the literature. The main problem, however, is that these approaches are inherently incomplete, and so they suffer from false positives. And so they give no help in knowing whether a safety property is actually violated, and if so, in determining the cause of the violation. All right, so this concludes my review. Thanks a lot for your attention. Let me know if you have any questions.